Okay, we're going to do some SolidWorks today. So normally this lab would be done with an actual tensile testing machine, and we would get a sample of the material we were trying to analyze, put it in the machine, perform this test on it, and get some data from that. But since we can't actually go to the machine, we're going to simulate that. Now it's going to be a little bit almost redundant, because the thing we're trying to figure out in this particular case is the modulus of elasticity, and SolidWorks already knows the modulus of elasticities of the material that we're dealing with. So it'll be a little bit odd, but the simulation itself is pretty neat to set up and to watch. So here's what we're going to try and accomplish. This is a 3-point bend test, and 3 points because there are, one support here, one support on the right side, and then one loading bar in the center, and we're going to load it so that it deflects downward, something like that. So that's what we're going to try and build. So this would be a 3-point bend test, is what the name of it, hence the 3 points. You have your sample in there, and in this case we're just going to make everything out of steel, some generic steel material. So we're expecting to get a modulus of elasticity somewhere around 29 or 30 million psi for the modulus of elasticity. How we're going to go about doing that is, let's zoom head on here, let's turn off perspective for a second, is this looks a whole lot like the beams that we just dealt with, a simply supported beam with a load directly in the center of it. And we already know an equation, PL cubed over 48 EI, if you happen to remember it, for the maximum deflection, which would be right under the load for a simply supported beam with a point load in the center of it. So if we have that equation, PL cubed over 48 EI, P is just going to be whatever load we apply. L is going to be the distance between the supports. I is going to be the moment of inertia of this cross section, which is just a rectangle for what we're using here. And then delta, or y, or whatever you want to call it, the deflection, is going to be given to us by SolidWorks. It'll estimate the amount of deflection that we have. The only variable in that equation that we won't know is E, modulus of elasticity, so we could back out the modulus of elasticity. So this would be one way you could calculate modulus of elasticity if you had a sample like this one and an actual testing machine. You could do the exact same thing. Now, like I said, SolidWorks already has a value for the modulus of elasticity for all of these materials in our simulation, so it's a little bit redundant to actually back it back out of what SolidWorks already knows. But like I said, the simulation itself is interesting because now we have some contact that we have to deal with, and 4 different pieces, so it's a little bit more complicated than the last simulation we did that was just a tensile test. So let's see if we can build this and hopefully not have too many problems building it. Let's go actually to the paper and write out what we're going to build. So the beam is just going to be a steel beam. There's the cross section of it, and then we're going to have the length of it over here. I guess it would actually be that way, like that. So what I'm going to build will be a 1-inch wide. So that would be like, well, if I lay it down flat, the 1-inch would be this direction, by 1/8 of an inch thick, and 8 inches long. So this would be our little sample. So if we were actually doing this at a machine, we would cut this out of whatever material we were trying to test. Our supports over here, normally these supports in the actual machine would be round. I'm going to make them into hexagons just to make it a little bit simpler to model. Well, not simpler to model them, simpler to get them to interface with my flat beam here. So they have these flat edges on them. So they're going to be little hexagons. And I'll make them 3 inches long. So that's its side view. I will inscribe a circle here that is a 1/4 inch diameter. And like I said, this will be a 3 inch length. So we'll make one of these, copy it a couple of times because we actually need 3. It's a 3-point bend test. And one of these. So let's go over to SolidWorks and make those parts. Let's just get out of here. Check. And let's do new. What do I have open here? I've got all of these open. Let's close all the existing pieces so that we can start from scratch. We'll save all that stuff. All right, so we're starting from fresh. New part. Let's do the beam first. That's really simple to make. It's an extrusion. We'll make it on the right plane, and it is a little box, 1 inch by 1/8 of an inch, and we're going to make it 8 inches long. I'm already in inch, pound, and second. You can see that down here in the, oh, that's actually off your screen. Let's see if I can pull it up some. Down here in the bottom right, there's different unit systems. I'm in inch, pounds, and seconds. Now, I do need one other feature on here. I just changed to perspective mode because I like that better. I need a split line, or at least that's how I'm going to line up the center point, is on a split line here. So it's not going to actually split the part in half, but it's going to put a line across here. So to do that, I'm going to put a plane that's parallel to this one. And I want it 4 inches because remember I made the thing 8 inches long. So I want it 4 inches from this, but I want it the other direction. So I need to flip that. There it is right in the center. So now I have a plane there. And then I'm going to go in here to split line. And it already selected the plane. And then I'm going to split this top surface. And you can see it puts this little line right there on the surface. So now I've got the top surfaces split in half so that I can locate that center support. There's other ways to locate it. This will be a simple way to locate it for me. Let's save that part. Let's save it as, I don't want to rename, let's call it test beam. Actually, I've already used one called test beam. Let's do test beam 2 so that we have a new one. All right, let's make our supports. So a new part. These are going to be on the front plane. I'm going to put them right at the center, and they're just going to be hexagons centered on that origin. I do want them to, you can have them different directions, so I'm going to make it where it's the flats are at the very top and bottom. And then there's that circle. I'm going to use that to make it 0.25 inches. Okay. And then I said to make these 3 inches long. They're generally a little bit wider than the sample that you're using. So my sample was 1 inch wide. I'll make these 3 inches wide. I'm going to put a split line on the bottom of these pieces to help with alignment also. So I don't have to make a plane. There's already, the right plane is already right through the center of this since I made it at the origin. So I don't have to make a new plane. I'll use that one. So split line. You can't find the plane now. It's over here. So there's my, not the front plane. Not, oh wow. I'm in the, there we go. Right plane. And now we're in the, what do we want to split? I want to split this bottom surface. And there's that split line on the bottom. I should add material to these. Let's just do them as plain carbon steel. You can see a slight color change. I need to go back and do that to our beam also. Let's save this as support. I already got a support, so it'll be support 2. Now let's go back over to that test beam and give it a material also. So I'm just right clicking on material and picking plain carbon steel. There we go, we'll save that. Those are all the pieces we need. So let's make an assembly. New assembly. Okay. Let's bring our beam in first. And just put it somewhere. And now let's create some new components, the support. Let's put one here. And let's get it lined up. So here's what I'm going to use, that split line lined up with that split line. And I will mate those together so that way it's definitely in the center. It's a little bit difficult to figure out how far over to set because I can't click just the center of this face. So that's why I made that split line. I don't want it sitting over here though. I want it, you know, I want to, where do I move it? Oh wow, I didn't want to tilt the thing though. So let's actually get that surface to match with that surface. All right, now it won't roll around, but it can slide back and forth. So let's mate that end with that end, but I don't want them, you know, lined up exactly coplanar. So let's offset it by 1 inch, but actually the other inch. There we go. So now that thing is fixed in place, centered up on our beam. So that's good. Now let's insert another one of those and let's mate it to the bottom like that. So that's good, except it's, you know, we got to add some more mates. Let's move it over here, and let's do that same thing where it's 1 inch from the end, so it's centered. And then let's set it in 1/2 inch from the split line to that end. Let's set that 1/2 inch. So that'll leave some overhang for our little beam. And then we need to basically do the exact same thing again, but on the other end. So insert support here, mate the bottom of the beam with the top of the support, mate the ends 1 inch away from each other so it's centered, and then mate the split line and the end line. Let's make those 1/2 inch away from each other. All right, there's our little assembly of our 3-point bend. So this would be inside a testing machine with all of the load cells and everything. But this is all that we're going to need, hopefully, to simulate the same type of thing. So let's do File, save this assembly. This will be our test rig. All right. Now let's do the simulation part. So we're going to do a new study. We'll just do a static one. You could do other, I guess maybe like a frequency one and load it over and over, but we're just going to do a static study. Our parts, they all have check marks on them, so that means that they all have materials defined and they're ready to go. This component contact is set, if we open it up, it's set to global contact bonded. So bonded, actually I'll leave it this way, run the simulation and show what happens with bonded. But basically it means everywhere that parts are touching, so basically all the touching between the support and the beam is simulated like they're bonded together, welded or glued together. And that's not what we want, but I'll leave it this way for now so we can see why we don't want that. Fixtures, we need to fix, I'm just going to fix the bottom surfaces down here. So all those little green arrows are saying that these bottom surfaces can't move in any direction. So they're fixed on the bottom. And that would be more or less true in the simulation, I mean in the real world. Let's put our load on the top of this one. So external load, force there. I'm going to put 100 pounds on it, just as a number to deal with. The direction is fine. So we have a force, we have some contact, bonded contact, and we have a fixture. Let's go into mesh. Now, my computer has a little bit of trouble, so I'm going to create a mesh and create it a little bit coarser than the default. So whenever I'm trying to do all of the streaming and everything, recording and everything all at one time, the more fine I go with this mesh, it seems to have trouble. So we're going to go coarse so that it doesn't take forever. All right, we didn't get any errors. You can see these, it's a relatively large mesh, so the triangles here are the individual elements in our finite element analysis. They're actually three-dimensional. This is just one side of them. Let's run the study and see what happens. All right, didn't take any time to run this one with the bonded, but look what happens. See how it's this is not the shape you would expect for the simulation for the real world. You wouldn't expect this S shape. You would expect something, if we really had a beam on, let's draw circular supports. But if we have a beam that's just sitting there, we push in the middle, you would expect this shape to do something like, there's nothing holding this down over here. So you'd expect something like this. Just a smooth curve. But we got this S-shaped thing, and that's because of that bonded connection between the surfaces. All the contact is bonded. Now this one doesn't really make much difference because it is just applying the force down here, but with this overhang, this end actually should be allowed to kick up, not stay flat on there and make this weird shape. So we're going to try and fix that. It'll cause the simulation to take a little bit longer, but let's go into component contacts and let's edit. So I'm right clicking, edit definition, and I'm going to go for not bonded but no penetration. So basically they collide into each other and don't go through each other, but that not being bonded makes it a more difficult simulation to run. I'm going to add friction between them, 0.3 maybe, just a high coefficient of friction, but just so that there's some amount of sliding available. Maybe let's do it 0.2. All right, so it's telling me that, hey, I've changed the contact here. We're gonna have to remesh all of this thing. So let's go back to mesh, create mesh. Yes, it's going to get rid of my previous results. We're still on the more coarse side, so that seems okay. Let's see if it'll mesh it. It did mesh okay. The mesh looks more or less the same, except now instead of these surfaces down here being bonded together, they're in contact. All right, let's see if this will run. It should take, it's definitely not as instant as it was before. And the more contact you have, the more elements you have, the longer and longer these simulations are going to take to run. This one still shouldn't take terribly long, but it may take a minute or 2 minutes to simulate. So far we're at 24 seconds. I remember when I was doing my PhD, I was simulating contact, sliding contact on a fixture inside of a human femur, and obviously this was quite a while ago also, so the computing power was much weaker, but those simulations would take a day or more to finish running, and so you really wanted to get it right the first time. Here, if I have something wrong, you know, maybe we wasted a minute or two, but you can still have some really complex simulations even with today's computing power. This is not one of those, but you can still have hours of simulation time and then find out that you had an error in your geometry or something like that. Hopefully we will get this one to resolve, but there's a big difference between that sliding, those surfaces sliding past one another versus them just being bonded together. As you can clearly see, the bonded one was almost instant. If you're running this on a laptop, or a simulation like this on a laptop, it's generally a good idea to plug the laptop in, because most laptops, when they are running off of battery power, throttle back the PC. Hey, it's solved. All right. So it took about a minute and 45 seconds or so. I didn't see the actual time, but something like that. Anyway, it's a good idea to plug the laptops in if you're going to run a simulation on those, because in general, laptops throttle the CPU back about 50% or so when they're on battery power. And so it'll take even longer. So here's the shape we were expecting to see. There's that, it kicks up. Now there is a little bit of collision, penetration right here on this corner. I'm okay with that. We're not really worried too much about this geometry, but we also, the way I loaded the loading beam, I put the load all the way across there, and you can actually see a little bit of curvature in the loading beam. Now we're magnified 5.5 times, it looks like. So there's probably not that much. Normally the way this would look in a machine is that loading would only be right in the center of this little loading beam. At least most of the ones I've seen. Some of them have the beam fully supported, and there probably wouldn't be much bending going on in the beam, in the loading bar here. But this looks like what we were expecting. There's that curve. Let's get a head-on view of it. That looks like what we expect to see. Usually you go in and animate just to see, let's slow down, the animate is too fast. See if it looks more or less like what you expect. That looks reasonable. We would probably, if we were trying to get real data from here, we would probably run this simulation a couple of times. Let's go over here to the paper. We would probably run that simulation a couple of times and pick out the point of data that we're interested in and plot number of elements. So that's the, right now we have, let's see if I can see the mesh data. We have, I'm looking over here, mesh total elements, 3,279 elements. So that's those little tetrahedrons, the ones that look like triangles. And you would increase that number. So this would be an increasing number of elements. And then maybe you're looking for a stress or a displacement or whatever. We're looking for a displacement. And what you want to see is something that converges. So as you increase the number of elements, and I'm probably exaggerating here, but it helps to exaggerate it, you get something where it looks like your models are converging to giving you the same number over and over and over again. And it could be converging the other direction too. It would be just as fine if it converged this way, right? What you don't want to see is something that's just taking off or oscillating back and forth and things like that. You'd want to see, this is kind of one way that you can verify a model with its own self, because you might be tempted, well, my computer is really powerful, I've got a supercomputer, I'll just run the number of elements up to the maximum I can do, let the simulation run for an hour, and that should be right. But it would still, even in that case, you want to make sure that the model itself is predicting the right kind of behavior. And it's good to do a couple of runs at a low resolution, a medium, and a high, and see if there's some converging happening between those answers. Because it might be that you're just in this situation, you ran the elements all the way up to the maximum, you just maxed out all the simulation parameters, and you've got this data point, but you don't have any history of if you converge to that data point or if you are diverging or something. So that's a good, relatively easy way to have a model check against its own self. All right, now what am I going to do with this data? So what I want is I want to know how far this thing has been. It does give me a displacement plot right here. I actually want to specify my own though. So I'm going to go to results, right click, define a displacement plot. And it looks like Y direction, looking down here, is the one that is the main displacement I'm looking for. So I'm going to make the Y displacement. I want it in inches because everything else is in inches that my model is using. I normally like to display it in floating point just because that's easier for me to read. So there we go. It changed my scale. Now I'm at a true scale. I think I had it clicked to true scale. So this is what I would really expect to see in the machine. And I could read off the chart here, but I actually want to plot it. So I'm going to right click on my new displacement chart and do a probe. And I'm going to probe on a selected entity. And I'm just going to select this line as the entity. Update that and plot it. Well, so that's backwards. Let's flip it. So plot it. There we go. And that looks like what I expect that line right at the top of my beam to look like. And so I can see the amount of deflection. So actually there's the 0 line, and some of it kicks upward. That's that little part that's overhanging. And then all of this is deflecting. Now, so that looks good. If I look in my little summary over here, I've got maximum and minimum amounts of deflection. So negative 0.144 inches. It's going downward in the opposite of the positive y, so it's a negative number. So let's write that down. Delta max, and now they call it min because it's a negative number, but it's the maximum deflection that I'm interested in, is equal to negative 0.144 inches. Okay, now let's go to MathCAD, I think. Let's see, I think I have it available. Bring it into view. And remember, we have an equation of the elastic curve for a simply supported beam with a point load in the middle of it that says delta, or I think they say y, but I'm going to use delta max equals, and it's negative, P times L cubed divided by 48 times E times I. So we know a lot of these things. So delta max we just found is equal to negative 0.144 inches. That was created by a force P that was 100 pounds. The length of the beam, now we made the beam itself 8 inches long, but remember this L is the distance between the supports, so we'd have to go back to the charts to look at this PL cubed over 48 EI equation to see how they're measuring L, but it's the distance between the supports, which for me, it would have ended up being 7 inches because I made an 8-inch long beam. I moved each support in half an inch, so that's 7 inches of support, or between the supports. I is the moment of inertia of the rectangular cross-section of the beam. So it is base times height cubed over 12, where, yeah, I know, move out of the way. The base for this would be the part that's laying down flat. And in my case, I made that 1 inch. And I made the height of the thing, the height of the beam laying flat, 0.125 inches. So it's 1/8 of an inch. So that's everything in there except for E. So we should be able to back out E. E would equal, let's see, negative P times L cubed over 48 times I times delta max. And we could solve for E. It's in pascals. Let's put it in PSI. Let's make that into a, that's the right number, but let's make it into a decimal number. Or maybe a scientific number. No, that's, let's just do decimals. Actually, there's with engineering. That one works well. So 30 times 10 to the 6th, so 30 million PSI. So that is exactly where we expect a steel to be, 29 to 30 million PSI. Now, I didn't check, but remember we assigned a material to this beam right here. Let's edit that material. And look, there it is. Oh no, that's the tensile strength. Elastic modulus. Oh, that's in the wrong units. Here we go. Change our units to English. 30.457. We calculated 30.489. So, you know, pretty close, but the simulation used that number, used this number to predict this deflection to begin with. So, of course, it's going to come out very similar. If you were performing this in the real world, a 3-point bend test in the real world, you wouldn't know E. You'd have an idea of what it should be near based on what material you're dealing with, but you wouldn't know the exact number. And so this would be one way. Another way would be in the tensile test. If you recorded all of the data, remember, the tensile test would give you a plot with delta and force, that you could divide the force divided by that area of the tensile test specimen, which gives you sigma, and delta would divided by the original length would give you strain, and you get something like that. Modulus of elasticity is the slope of this line. So there's two different ways you could get modulus of elasticity. So the nice thing here is that you've used a lot of data points. You had to create a lot of data points to get this particular one, versus here we have one data point, right? And so we have one that might have some error in it, but from being only one data point. Now we could run this test over and over multiple times with different samples, and even 3 or 4 times per sample, and see if we could average out. But they're giving us the same pieces of information. Okay, so if you're in the course, if you're taking this course for credit, then I want this to be lab 2. Basically run your own version of this simulation. You don't have to use the exact same geometry, but it's totally fine if you do. It's probably easier to use the support bars as hexagons like I did, so that you can get them to mate with the flat bar simply versus trying to mate the round surfaces and all that kind of stuff. You don't have to make everything out of steel. Maybe you go in and make your support bars out of steel, but you could make your test beam out of aluminum or brass or copper, you know, whatever material you want to do. Back out the modulus of elasticity like we did with the equation of the elastic curve for a simply supported beam, the point load in the middle of it, and see if you get numbers that are reasonable for those materials. You can even check, you know, with the actual material you assign it, because it will tell you what the modulus of elasticity for that material is. It assumes it is 30 million or whatever it is, 11 million for some kind of aluminum, whatever. I think that should work. If you have trouble simulating this or meshing it, like several times I ran this and I just did right click, mesh and run, and it had trouble with the default settings and getting it to mesh just right. So you might want to back off on the mesh size if you have that kind of trouble. That seemed to solve it for me. Also, I originally went in and defined my own contact sets, but it seems to work fine if you edit this global contact and switch it from bonded, which is the default, to the no penetration version. You can add friction coefficient if you want to, or just leave it blank and it doesn't change too much, because it's not really set up to slide one way or the other, although as this beam bends it does pull inwards a little bit on these corners right here, so there is a little bit of friction. All right, set one of these up. I'm not going to have this due, if you're taking this for credit, I'm not going to have it due on Monday. That's too fast of a turnaround. Monday's actually an exam, so work on this and we'll have it due the next Monday. So I think that's the 27th maybe. All right, I will see you guys, well, actually Monday, and we'll be doing an exam too. So there are also some practice exams and web work problems, all that kind of stuff. Practice exams on Moodle. You know where the web work problems are. And let me know if you have any questions.